Welcome back. This is the fourth chapter of Lecture 9 in Biomedical Signal Processing. Now I will talk about the other method, the analysis method, to get sparse solutions. So in this case, as I have told you, you are starting from a zero coefficient vector, and all the way along you are taking care of having a solution which fulfills, which corresponds to your measurements and which is sparse. How could we do it? There are some methods which I have listed here. The first one is the matching pursuit. This is a greedy method. We will see it in detail. Then what you could also do, which I have already kind of mentioned, is that when you have like the L0 norm, you relax it to a higher order problem. So instead of L0, you solve an L1 problem, and then it will make your life a lot easier. Then you can also use basis pursuit algorithm, which is a type of linear programming to have this sparse solution. And finally, what I had written is using some general optimization techniques. We will see what I mean by that too. So first of all, this greedy optimization method. Imagine the following task. So you are at the shop and you have to pay for 100, let's say a 36 something. So let it be in euro or whatever you would like to. And you have some coins. And you would like to pay with the least coins possible. So you would like to have a sparse solution. What you would do in a greedy method is, okay, I have to pay for 36 something. So I take the largest coin which fits this sum, which would be the 20. Okay, 20 fits. Then from the 36 I subtract the 20. There is 16 remaining. What can I fit next? It's a tenner. Okay, I have 6 left. What can I fit? A 5. Okay, and finally a 1. So you will use only 4 coins, and you have, in this case, an optimal solution. This solution will not always be optimal. Not in case of the coins, but in other problems, it won't be always optimal to use this method. So what does it mean from a signal processing point of view? What does it mean for our algorithms? So you have a signal measured and you would like to make it sparse. So you have your signal, you are 36 something, and you are starting from nothing. So you take your wavelet basis and you check which of these basis vectors is most similar to your signal. So which fits it the most, which will be like a simple scalar product, which has the highest product with your original signal. And you pick that signal, use that coefficient, so their product as a weight, and then you add it to your composed signal. So coefficient times the chosen basis vector will give you the first brick of your composed signal. Then you subtract this composed signal from your original signal, and you check what is fitting the best now. So again, you check with this remaining signal which basis vector is the most similar, which is fitting it the best, and then with the coefficient, so the scalar product, this highest number, you multiply it by it, and this will be the second brick to your composed signal. So you are adding them up, and you do it until you reach a limit. What limit? Until you are similar enough, or until you are using too much basis vectors. So you would like to keep it sparse, to use not all 1000 possible basis vectors, only 50 of them. You can stop after that, or you can stop when you think their norm is similar enough. So the composed array is very similar to your original signal. So this is the greedy optimization, the matching pursuit algorithm. There is a pair of it, the so-called orthogonal matching pursuit. In this case, a very simple thing to do is to use the Gram-Schmidt orthogonalization on your basis vectors. And in this case, you will have a convergence very fast. So if you have this orthogonal basis, then you will have a very good convergence, which is good from a programming point of view. But what is not so good for us is that these arrays doesn't really mean anything for us. So when you would like to go back to your original basis, using the backward solution for this Gram-Schmidt orthogonalization, so when you go back to your original basis, then you will not have sparse coefficients. So in this orthogonal basis, which you have created with the Gram-Schmidt orthogonalization, you do have a sparse solution and the best possible solution. But if you would like to get some meaning out of it, so you go back to your original basis, then your coefficient array won't be sparse anymore. So you are losing this feature of it. So it could be an interesting idea to consider if you're dealing with such a problem. Then another possibility which I have mentioned is the so-called basis pursuit problem algorithm. This is a linear programming technique, and here you are always having regularizers which are inequalities. So these are the ones you are dealing with, and you are projecting between half planes, and this is how you can solve this problem. It is written here in the description how to do this. You won't be asked to do this in the practice, but it can give you some idea if you would like to go on with this type of algorithms. And here you can see some comparison between the two methods, and here you see the matching pursuit algorithm where you would like to have this grayish signal, and first of all you find this black component of it, and then you are adding it up until you have the whole signal. Now, this was when you have your problem and you have one regularizer which is somehow easily solvable. But we do not always have easily solvable problems to minimize. So until you have only one regularizer which is convex, you are good to go. But what if you have multiple regularizers? Then the problem will become more and more difficult to solve. So there is no easy solution to it. You have to handle it somehow differently. And alternating direction method of multipliers, called ADMM, gives you a framework for solving optimization techniques, difficult optimization techniques, in an easier method. So here you have some regularizer which is too complex to solve. So you do not know any analytical solution to do it. Somehow you should get rid of this part because you cannot solve it. You cannot solve this minimization. So what this framework does is that it splits your variables. So originally you have this coefficient array which we would like to fulfill the data fidelity term and the regularization term, and you split it into two. So you say that I say x becomes g. So instead of x in the regularizer term, you simply write g, a new variable. You have some knowledge about it, but now you can handle them differently, not simultaneously. So you will rewrite your original equation. This is the so-called augmented Lagrangian form of your minimization problem. So you have the original data fidelity term, you have this modified regularization term, and you have some connection between these two. So this will be a penalty term, not to let x go too far, dwell too far away from g. So really keeping them similar, because you do know that actually they are the same, but now you're handling them differently. So you have to stick them together, keep them together, and this is what this penalty term is for. And this is the Lagrangian part of the equation, which I hope you have learned about the Lagrangian equations. If not, it is explained in the description below. So once you have done this, you can split your problem. So what you do is, I have x in this first term, and I have x in this these two last terms. So I put them into one problem, and I put everything which contains g into another problem. So here you see it. Here are the bits containing x, and here are the parts containing g. So first you minimize for this equation, which will be usually easier to solve than the original equation was. Then you minimize for the second part, for g, in this equation. And then you are updating your Lagrangian, which is the third step. And if you are iterating between these steps, then it will give you a solution. So this is this ADMM framework, which helps you to handle more difficult problems in optimization techniques. So these were the methods we could use to actually have a sparse solution. And as I have told you, that this is a good way to filter noise from your signal, but for other techniques as well we have discussed before. And thank you for your attention.